So now let's move on to one of the big important questions that we want to pose here near the end of 3.7, which is, what if I went back to this integral of e to the negative x squared? That's notoriously difficult, right? We spent the whole last section talking about it. But notice here I've set up an improper integral. Technically, this is equivalent to the integral from 0 to infinity of e to the negative x squared. And the question that I have is, does that integral converge to a finite number? That is the area underneath here going to be finite? Well, notice that's going to be really difficult to determine if I can't find an antiderivative, right? So how am I supposed to do that? Again, I'll just write here that this is difficult since f of x equals e to the negative x squared has no easy antiderivative. That is, no antiderivative that can be written with elementary functions. So yeah, what am I supposed to do with that? Well, this is where we're going to have to develop a bit more powerful machinery to try to tackle this sort of a question. On the next page, you'll see that I have written out the comparison theorem. And this is going to be a very, very important theorem for us to conclude this section. Let's see what it says. Suppose that f and g are continuous functions, but they aren't just any functions. They have to meet these criteria. It has to be the case that f, which I'm going to label here as a blue function, is going to be greater than or equal to g of x, which I'll label as a red function. And they both have to be greater than 0. Now, this doesn't have to be true all the time, but just for some time past a certain point. Well, let's take a look at this in a quick picture. Let's suppose, for the sake of argument, that my blue f of x function looks like this. Okay, there it is. This is my f of x. We'll assume that it's starting right here from a. We all only care about what happens when we get past a. Now remember, g of x has to, so now g of x needs to be less than or equal to f of x. So if I was to draw it, it would be fine if these things became equal for a while, but ultimately g of x has to remain lower than or the same. Now, once I have these two functions, I can start to think about some interesting questions related to the area underneath each of their curves. Let's really quickly think about what we could possibly say if I asked us to calculate the area underneath f of x from a to infinity. Well, I would obviously be able to maybe set up an improper integral and crunch some numbers and some limits out, and let's suppose that this answer came back convergent. That is, there's a finite amount of area underneath that blue curve. Well, I might then be able to see what conclusion I can draw. If I look at these two pictures, automatically I might be able to see which curve would we expect has more area under it total. Well, it might seem like the blue curve, right? Because it's higher up, so it's got more area beneath it. So if I expect the blue curve to have more area than the red curve has under it, and I know that the area underneath the blue curve is convergent, let's say for the sake of argument, underneath the blue curve there's area 10, then underneath the red curve, doesn't there have to be less than 10? So with that, I could then say that the area under g of x is also convergent, right? It's also got to have some finite amount. Maybe it's got area 8. Notice, though, that there are some other determinations I could make here. Let's suppose that I started off the problem a bit differently. Let's suppose that I instead calculated the area underneath the red function, that is our g of x, from a to infinity. And let's suppose that I found that it was divergent, meaning that there's an infinite, maybe say, amount of area underneath the red curve. Well, again, since the area under the blue curve I would expect to be more, then I certainly can't have a finite amount of area up above. So I could definitely then conclude that the integral from a to infinity of the blue function, f of x, is also divergent. Now, It's super important that you spend your time trying to think about this scenario. A lot of times people will make very, very, very poor assumptions when they come back and they review this theorem. And you can double check yourself right now. This theorem does not say that whatever one thing does, the other thing does. That's not what it says. It doesn't say if you get convergent, you automatically get convergent. No. It said if the area underneath the blue function is convergent, then you can make a determination about the red. And if the area underneath the red function's divergent, then you can make a determination about the blue. Notice that if I was to kind of reverse the order of these statements up here, I wouldn't be able to get something that actually or I wouldn't be able to get like a good conclusion. I wouldn't be able to reach really any sort of conclusion. Let's see how that works. Let's suppose that I found that the area underneath the red curve was convergent, like maybe it's got area 5. I know that there should be more area underneath the blue curve. So what's a number or a value that's more than 5? Well, maybe 10, maybe 500, maybe infinite. I have some options that are convergent and other options that are divergent. So if the bottom area happens to be finite, I don't know anything about the top area. I can't reverse the order of that first statement. Similarly down here, if I have the area underneath the blue curve is divergent, so I know that the area up here is maybe infinitely large. All I know down here is that the area has to be less. Well, that means that I could have, again, like an area of 6. But I could also have an area of infinite, maybe just like a slower growing infinite amount. So I can't reverse the order of these statements, and I have to think very carefully about which one is applying in a given context. Now in the next video, we'll take a look down here at example 6 to see how we can use this theorem to actually show that the integral of e to the negative x squared from 0 to infinity is actually convergent.